Okay, so let's look at this next example here. So notice, one of the things that we're going to be doing is I'm going to be giving you a function defined from, let's say, in this case, 0 to 1. But it could be 0 to something else. And I'm going to want you to sketch the Fourier cosine series, the Fourier sine series, or perhaps I'll give you a function from minus L to L, and you'll want to sketch the function, the full Fourier series. Okay, so we're going to look at 0 to 1. And the function that we're going to look at is going to be a simple function only because graphing it is going to be hard otherwise. So we're going to look at the function. It's going to look something like this. This is 1/2. I'm going to write 0.5 because I want to. This is 1/2, and this is 1. And actually, let me say this is 2. And then this right here, roughly, halfway, this is minus 1. And so what the function is going to be, it's going to be this from 0 to 0.5, and then here, it's going to be like that. In terms of Fourier cosine and sine series, it doesn't matter too much, but just to have things defined properly, well-defined functions, we'll say it looks like this. Okay, and so here's where here's where things get a little more complicated, and it's going to let me talk a little bit more about this average value thing. Okay, so let's start with finding the Fourier cosine series. So for the Fourier cosine series, remember the first thing that we're going to need to do is to find the even periodic extension, and maybe the 0th thing we'll need to do is to look at, to put these axes, or to label the axes. So this will be minus 1.5, and this is minus 2. Okay, so nothing here is really to scale. This is 1.5, and this is 2. Okay, so let's look at the cosine series. So step 1, find the even extension. Okay, so this part is just going to be like that, and that's where the value there goes. And then from minus 1 to 0.5, we'll have something like this. Okay, and now if I want to extend this, so I've got minus 1 to 1. I guess I really need to extend this, so my gaps here are getting too big. So whether or not it's to scale isn't so important, except I need there to be enough room to do what I need to do. So this is 1.5, this is 2, this is 2.5, and this is 3. Okay, so to see what it's going to look like from 1 to 3, I'm just going to copy and paste this graph and hopefully do it properly. So from minus 1, from 1 to 1.5, it's going to be this part. Then from 1.5 to 2, so open there, from 1.5 to 2, it's going to be this sort of parabola-looking part. Then from 2 to 2.5, it'll be the other part of the parabola. And then from 2.5 to 3, it'll be like this. Okay. All right, and this is minus 2. This is minus 2.5. And this is minus 3. Okay, all I'm doing now is I'm just sketching the even periodic extension of the function that I was given. That's all I'm doing now. I haven't gotten to the point where I know what the Fourier cosine series will look like yet. I'll do that in just a second. Okay, but right now the thing that I'm sketching is the, Okay, all I'm doing now is I'm sketching the even periodic extension of the given function. And now to see what it is from minus 3 to 1, I'm just going to copy and paste this graph and put it there. And so from minus 3 to minus 2.5, I'll have this. Then the parabola part, I'm not telling you what the formula is, but it looks like a parabola to me. From there to there. Hold on. So this is down way too low because my numbers are way too low. Okay, so minus 3, minus 2.5. I wish I could do like the weatherman thing where I could kind of have a grid up here that I can look at on my monitor. I wonder if there's a way I can figure that out. Not for this semester though, sorry. Going from here to here. Okay, so again, I don't want it to look so deranged. I know it's weird that I'm spending so much time getting this one height right when everything else is so messed up. And then I'm going to have similar issues here. Okay. All right, and then, so actually from here to here, this part is filled in. Okay. All right. Yes, there we have it. Okay, so that is the even periodic extension of this function defined from -1 to 1. Okay, so let's say, so now I want to transform this graph into the cosine series. Okay, so the Fourier cosine series will converge to the even periodic extension where it's continuous. So in other words, like on the internal, like the internal parts there and there, there and there, it's going to converge. It's only going to be at the jump discontinuities where it doesn't converge. And at those points, it'll converge to the average of the two values. Okay, so let's look at maybe the first jump discontinuity we come into contact with, which is going to be between here and here. Okay, now the average of the value here is 2. So actually, let me start here. The average of the value here is -1. Okay, and I'm going to use strange notation. I'm going to just call this point generically A, so -2.5 is A. I'm going to call this number right here f of A minus 0. Okay, now literally f of A minus 0 means f of A, so this must mean something more. This must be an idiom for something. And it means the limit from this way. Okay, like this is A minus 0, so if I have something like f of A minus 0, this is equal to the limit as h goes to 0 of f of A minus h. And h is positive, so it's going to 0 from the positive side. So I'm doing f of A minus h, so it's like this is A minus h, and this is what happens, I get closer and closer and closer. At any rate, this is going to be the limit there. Okay. And the value here, okay, is going to be plus f of A plus 0 with a similar definition. That's going to be the limit coming from this way. So this is the left-hand limit. F of A plus 0 is the right-hand limit, and it's going to converge. The cosine series will converge to the average of those two. Okay, so the average here is -1. So I'll do the computation down here. The average here, or the value, the left-hand limit here is -1. The right-hand limit here is 2. We're going to divide that by 2. So -1 plus 2 is 1, so this is 1/2. So the Fourier cosine series will converge to 1/2. So it's not going to converge here. The Fourier cosine series won't converge to that point, or to that point. It will converge to 1/2, which is this point. Okay, if I look at the next discontinuity, if this is my A, same thing. It's going to be equal to the average value of the left-hand limit plus the right-hand limit. The left-hand limit is 2. The right-hand limit is -1. 2 plus -1 is 1 divided by 2 to get the average is 1/2. And so we see these jump discontinuities, the series will converge to 1/2. So let me do something like this. Okay, so we can make an observation now. And the observation is basically going to go like this. So if I just care about the function from 0 to L, the Fourier cosine series is going to converge to the function from 0 to L, except at points of discontinuity, and at those points it'll converge to the average. Okay, so in particular, if I have a function that's continuous from 0 to L, the Fourier cosine series will converge to that function from 0 to L. Now, sine, the story will be a little bit different, as we are about to see. Okay, so this is the Fourier cosine series. This is a sketch of the Fourier cosine series. And doing something like this is a very similar problem to the homework. And doing something like this would be something that I would expect you to do on an exam as well. To be able to do something like this. Okay, so I'm going to pause the video for a moment and try to erase just the cosine stuff, and then I will do the sine series. So maybe I can be cool like Kenji Lopez alt and snap and do like I'll be back in just like that. Okay, I don't know if that worked or not. I could also be more like him and do a point of view thing and have it on my head and be kind of shaky, but not so shaky, not as shaky as you expect. I could be like, well, my daughter wanted me to make chicken curry, and we actually found at the test kitchen that if you breathe on the curry spices, the nitrogen in your breath will actually make it taste a lot better. Anyway, sorry, I don't know what I'm doing. So the problem is when I don't have students in front of me to keep me on task, I just go a little bit haywire. And that was one example right there. If you don't know who Kenji Lopez Alt is, that was especially bizarre. If you do know, well, I hope at least you understood what I was doing. And if you don't know, maybe you'll look him up and get some good food ideas. I particularly like, so he has these two videos where he talks about bolognese, one kind of a very complicated way, and one way a very easy way. And I very much like the easy way. It's very good. Anyways, I don't know why I'm so chatty right now. Okay, so now we're going to do the Fourier sine series. All right, so step one is we are going to compute the even, or find the odd, sorry, not even, we're going to find the odd extension. So we're going to start, if I look from minus 0.5 to minus 1, the odd extension is going to look something like this. And then if I look from minus 0.5 to 1, so this is 1, so now my scale is all screwed up. So hold on one second. I didn't anticipate this before I did I was more worried about snapping at the camera than I was getting this correct. Okay, so now we'll have something like this. 1, so this is 2, that's still 2, I don't know what else changing there, and this is 1. Okay, and so now from minus 1 to 0.5, the odd extension here is going to be like this. Okay, and again, when we do the odd extension, we don't know, actually we do know, I think I said we had something like this. Okay, so for the odd extension, we do know exactly, the periodic extension, there'll be some ambiguities. So we'll have this, and open there. Okay, so now I'm going to do the periodic extension of this. So as I go from, I'm just going to copy and paste this. So if I look from 1 to 1.5, it's going to be like this. Okay, now here's where we'll have the ambiguity. I don't know what's going to happen there because it's just the odd periodic extension is not well defined there. And now as I look from, okay, so for the next part, okay, so I have this, then it'll be this part here. So this is okay, it'll be like that. Okay, and then the other part like this, and then from running into the same problem over here, so this is 2.5, this is 3. That will take the value, and then again, due to the ill-definedness of the odd periodic extension, I don't know what it's going to be there. Okay, so this is, oh, sorry, let me do the odd periodic extension over here as well. So we'll have this like that. Like this. And then again here at minus 1, there's an ambiguity on what value the odd periodic extension should be taking. And I realize I made this. Oh boy. So this should be at, all of these should be at minus 1. Okay, so that is the odd periodic extension of this function here. Okay, so now I want to know what the sine series converges to. Well, I have the odd periodic extension, except for some of these where it's ill-defined, and the Fourier sine series is going to converge to the odd periodic extension wherever it's continuous, and it's going to converge to the average value where it's discontinuous. Okay, so let's look here. The function is equal to the right-hand limit is equal to 2, or sorry, the left-hand limit is equal to 2 here. The right-hand limit is equal to minus 1. 2 plus minus 1 is 1. We take the average, we're at 1/2. So the sine series is going to converge to 1/2 there. Okay, but notice what happens here. I've got the function is equal to minus 1 here, or sorry, the limit is equal to minus 1 here. It's equal to 1 there. Minus 1 plus 1 is 0. Divided by 2 to get their average value, you get that. Okay, where's the next discontinuity going this way? We're going to have something similar. This is minus 1. This is 2. This is minus 1. Their average is 1/2. So we're going to converge there. The limit here is minus 1. The limit here is 1. So their average value is 0. And then here, the average value will be 1/2 again. Okay, so in particular, what we get is the Fourier sine series, if I look from 0 to 1, is going to converge to the function at every point except for 0.5 and 1. We already know at 0 and 1, or 0 and L, it has to be equal to 0, just by the nature of the sine functions. So what's going to happen, the only other place of interest is going to be at this jump discontinuity where it's equal to the average. Okay, so for the Fourier cosine series, if I just want to kind of look at 0 to L and state a theorem just from 0 to L, Fourier cosine series will converge to f on 0 to L, where f is continuous, and to the average otherwise. Okay, the average meaning the average between the two jumps. Okay, but in particular, it's going to converge at 0 and L. So the only place that a Fourier cosine series will fail to converge from 0 to L is going to be where the function that we're interested in has a discontinuity. Okay, now the Fourier sine series will converge, I'm going to write this, converge to 0 at 0 and L, and will converge to f on 0 to L. So notice I'm not including 0 or L in this interval, and will converge to f on 0 to L, where continuous, and otherwise it will converge to the average. And again, the average meaning the average of the jumps. Okay, so this gives you enough information on how to sketch Fourier cosine series and Fourier sine series from 0 to L. In the next video, we're going to look at full Fourier series, and then in the video after that, we're going to look at why we care about cosine and sine functions. But hopefully you already have a good idea about why we care about this.